Have you ever been sprayed by a skunk? The legendary stench of skunks is all due to a class of organic molecules we call thiols. So thiols, as that OL ending suggests, are quite similar to alcohols. They're actually the sulfur form of alcohols. So instead of our OH group attached to our carbon skeleton, we have an SH group instead. Now our sulfur, our S here in our thiol, is in the same group as oxygen, so that means it also has 6 valence electrons and behaves relatively similarly to our oxygen. Right? So we still have our 6 valence electrons making up 2 lone pairs and then 2 covalent bonds, 1 to our hydrogen and 1 to our carbon. In our naming, we're still going to have that OL ending for, that we have for our alcohol, but we're just going to have a TH in front of it, and we're going to end with a thiol for all of our thiol-based compounds. Now, although we do share some similarities with alcohols, we're also going to see some key differences between our thiols and our alcohols. The first key difference between our thiols and our alcohols is in their acidity. So as you may recall from our first semester of organic chemistry, our thiols are more acidic than alcohols because, of course, they have a larger atomic size, which then creates a weaker bond between our sulfur and our hydrogen. Which then, of course, leads to a easier deprotonation reaction to make that thiol more acidic. So if we have a thiol versus the conjugate base of an alcohol, our equilibrium is going to strongly favor our thiolate, the conjugate base of our thiol, and our alcohol. Right, again, our thiol is a much stronger acid. Again, of course, this changes the properties of both our thiol and our thiolate. Right, as a weaker base, our thiolate makes a great nucleophile, right? So we can use this specifically for SN2 reactions when we want to avoid E2 reactions because it's not as basic. When we compare that to our alcohol and the conjugate base of our alcohol, our alkoxide, the alkoxide, remember, is a very strong base, and so it will tend to favor elimination reactions more than our substitution reactions. The second key difference between thiols and alcohols is in their oxidation reactions. Now, of course, with alcohols, so we typically see our oxidation reaction where we go from our alcohol and then we produce a carbonyl compound, right? It could be either an aldehyde or a ketone depending on the substitution pattern of our original alcohol. Right? So we can take that primary alcohol and create our aldehyde, which is essentially our primary carbonyl. So you might expect then that if we take our primary thiol, so we have our carbon with our single bond to another carbon, our thiol group and our 2 hydrogens here, and if we add oxidizing conditions, you might expect to form a thiocarbonyl where we form a double bond to our sulfur. Right? It's getting oxidized in the same way that our alcohol does. However, this doesn't actually tend to occur. Our thiocarbonyl compounds are very rare. This is because, of course, our sulfur, as we just said, with its higher acidity, makes a great nucleophile. So it's going to actually react as a nucleophile with our oxygen and create a variety of sulfoxide-based compounds. So as we react our thiol here under oxidizing conditions, we're going to end up with our sulfur acting as a nucleophile and adding on OH groups from our oxidizing agent. As we continue to oxidize our thiol, we're going to continue to add on our oxygens until we eventually create a sulfonate with our multiple oxygens attached to that single sulfur group. So we end up with our 3 oxygens bonded on there. Again, of course, remember that sulfur can break the octet, so we can actually have more than our normal 8 electrons on here as we're adding on these additional oxygen bonds to our sulfur rather than to the carbon itself. Right? So the sulfur ends up getting oxidized, whereas the carbon doesn't change its oxidation state throughout this reaction. Right? It started with a single bond to our sulfur, and it actually ends with a single bond to our sulfur, and our sulfur ends up getting all of the oxidized oxygen bonds added on. Now there is one other interesting oxidation reaction that can happen with thiols, and this occurs when we have 2 thiols that are reacted together in an oxidation reaction. So we take our 2 thiols, I'll use indicators here to indicate that these could be 2 different carbon chains, and if we react these together under oxidizing conditions, we can actually link these 2 thiols together and form what we call a disulfide. These disulfide functional groups aren't particularly useful in our organic laboratory, but they're actually incredibly useful in biology. So using this disulfide linkage, we can take 2 thiols that might be on very different points of our large biomolecule structure, and we can link them together through this simple oxidation reaction. So there's a variety of different proteins that will use this to then create very interesting 3D shapes just by forming those covalent bonds between different points of the carbon chain of that protein. So it's very useful for protein structure. In fact, if we add a reducing agent and we try to reduce our disulfide back to our original thiols, this will actually destroy our protein structure, and in many cases it will completely shut down that protein and prevent it from carrying out its normal biological function. So this particular oxidation reaction is incredibly important for our biochemical systems. So while our thiols do have a lot of similarities to alcohols, they still have kind of that same nucleophilic nature, and they do some similar reactions to our alcohols. They do have some key differences that will allow them to be used in different ways, particularly in our biological scenarios. Right? So they have a little bit of different nucleophilicity. They also have slightly different oxidation reactions that allows us to use them in different ways. While they're not super common, they do tend to be very useful molecules overall.